Today, I'm going to be talking about some work that I've been doing with my advisor, Gentner, and our collaborators, Ben G, Brian Matlen, and Sean Jung, on how spatial alignment can support visual comparisons. So, so in this talk, I'm going to start by just talking about how important visual comparisons are for learning, especially in STEM, the science, technology, engineering, and math disciplines. And we know that visual comparisons are really beneficial for learning and reasoning, but we also know that they may require support for people to actually get those full benefits. And then I'll talk a little bit about some evidence about how visual comparisons we think are carried out by a process of structure mapping, and then discuss a little bit how thinking about it that way can provide some insight into how we can support these sorts of visual comparisons and support learning. And in particular, I'm going to be focusing on the spatial alignment principle, which is derived from structure mapping theory. And I'll be discussing two completed studies we have that suggest that it's an important consideration in STEM education. And then hopefully, if there's time, I'll also talk a little bit about some ongoing work we have extending that. Okay, so moving right along. So as I said, visual comparisons are really important, especially in STEM. They're pervasive in lots of things that we do. So for example, comparing graphs of maybe different groups of people, different conditions across different time points. That's something a lot of us probably do very frequently. But there's also all kinds of other visual comparisons we have to make when we're in various STEM disciplines, things like comparing different representations of the same kind of thing, comparing different examples of a phenomenon, comparing different kinds of processes. These are just really integral and key to learning and reasoning in STEM. So just to talk through one example of how comparisons can benefit learning and reasoning, this is a study that was done by Gentner and colleagues at the University of Chicago. This was done at the Chicago Children's Museum. So you can see here, this is like a picture of the museum. And it was done as part of an exhibit on skyscrapers. So children would come to this exhibit with their families, and one of the activities that they were asked to do, or that they could do if they wanted, I should say, is they could try to build their own skyscrapers out of sort of these, I don't know if you guys, how well you can see these, but these sort of erector set type pieces. And what the museum was finding was that children and their families were not actually great at building stable buildings, right? They were building structures that were collapsing, they weren't stable, and it seemed like they weren't really very successful at understanding how to make these sort of tall buildings structurally stable. And so, excuse me. So Gentner and colleagues in this study were asking whether they could use comparison to give children and their families some insight about a key principle underlying stability. And so what they did in this study is, before parents and their children engaged in this skyscraper building activity, they pulled the children aside and gave them a brief comparison. So they showed them two buildings like these two here, and they asked the children which of these buildings is stronger. And whatever the children said, whichever one they picked, they then showed them, if they sort of wiggle the buildings, but the one on the left would deform and collapse, whereas the one on the right would stay upright, right? So then you ask the children again, which of the buildings is stronger? And children now, of course, know that it's this one on the right that is strong, that's stable. But the question is, do children have any understanding of why that might be, right? Do they have any sense of why this building stayed upright and the other one didn't? And if you are wondering that as well, the key difference between these buildings is that this piece here is set at a diagonal, which creates a brace, it creates a triangle, and that's a very stable structure. Whereas in the other building, the same piece is just a horizontal cross piece, so it doesn't create that diagonal that gives stability to the building. But do children have any sense of that? So after receiving this comparison, children went with their families to build the skyscrapers on their own. And then after that experience, to see whether children had kind of gotten anything from this comparison, they brought children back and gave them a new building, a new structure, this sort of cube here, that was also unstable. And they gave them a piece and asked them, where would you put this piece? How would you put it on the building to fix it, to make it stronger? And what they found is that children who had gotten this really brief comparison before the activity were more likely to put that piece on a diagonal, creating a brace, than children who hadn't seen that. Gosh, sorry. So this is just one example of many. Here's a list of some more, but again, it just doesn't even scratch the surface really, of examples of comparison benefiting learning and reasoning in various ways. So comparing examples facilitates word learning, it supports category and schema formation, retrieval and transfer. There's evidence of it supporting learning in science and math. The list really goes on, but I only have so much time. And of course, comparison also supports other learning processes that are really important, like self-explanation. So comparison is really powerful. It's really broadly, generally applicable. But we also know from all this previous research that learners really need support to fully exploit these comparison opportunities. So for one thing, you have to actually make a comparison, right? So just because you should compare things doesn't mean that you necessarily will. So that's one barrier already to getting a benefit from an opportunity to compare. But also once you try to make that comparison, you also have to kind of do it successfully. You have to do it in a way that you're aligning the examples you're comparing to actually get some of those important insights out of it. So we know that children need support, and the question is, what do we do about that? So just to give you an example too, to show you that comparisons are not all created equal, here are the buildings that I showed you before from the museum study I was just talking about. And the experimenters actually gave two groups of children different pairs of buildings. So some children saw the buildings I showed you before, which were highly alignable. So they were really, really similar. Really the only difference between them was in the orientation of this sort of key piece, making that information really salient. But another group of children got two buildings that, while they also differed in sort of the orientation of that key piece, there were also a lot of other dissimilarities between the building, which made it a lot harder to kind of compare them, align them, and see what was alike and different to really hone in on this important difference here. And what they found was that it was really only the children that got these highly alignable buildings that benefited from the comparison. So the support for that alignment from the overall similarity of the two buildings enabled children to kind of get an insight out of this pair that they weren't able to get out of this pair because they didn't have that sort of additional support for that comparison. So why is it that some comparisons work better than others? And how do we figure out how to support visual comparisons if that's the goal? Comparisons are really useful for learning, but they have to be sort of done successfully. How do we achieve that? And to answer those questions, I think really what we need to think about is what we're actually doing when we make a comparison, right? So how are we actually visually comparing? What is the process that underlies that? And you will all be shocked, I know, to discover that I think it's a structure mapping process. So for those of you who are unfamiliar with it, structure mapping is a process of aligning two examples by sort of putting elements in correspondence based on the the shared structure, the shared relations in the two examples. So for instance, in our buildings here, we have, this is like not a real representation of how these buildings are represented, but you have sort of structure in these buildings, you have sides that make squares here at the top and also at the bottom. You also have sort of this relation of one square being above the other one. And we also have these individual pieces. And in structure mapping, you sort of put these things into correspondence, right? So these bottom squares go together, the top squares go together. The fact that this one is above the other one is also something that gets aligned. And of course, then having made that alignment, it also becomes clear that this piece goes with this one because they're both sort of an interior piece of the top square, right? They're sort of playing the same role in the structure in the two buildings. In structure mapping, it also prioritizes a coherent set of correspondences. So it's not just willy-nilly any relation that matches. Like we don't put this sort of top square with this bottom square because they're not playing the same role in the larger structure of the buildings, right? So it's governed really by these sort of deeper, more coherent structures. And even though structure mapping really prioritizes structure and relationships, it is sensitive to object and property similarity. So for instance, here, considering the two pairs that we were just looking at, one of the reasons that these pieces were put in correspondence in this pair is because they're just generally overall very, very similar to one another, right? So they look really similar along with the structural similarities, but there are a lot of perceptual and structural differences in the bottom one that make it just harder to align because they're not getting this sort of overwhelming perceptual similarity to support the alignment. Okay, so just to provide some evidence for structure mapping as the process underlying visual comparison, I have some demonstrations for you. So I'm going to give you a task. This is the task from Sagi et al. And I'm going to show you two arrays of colored shapes on the next slide. And I want you to just determine whether the color of this shape, the sort of upside down triangle, is the same or different in the two arrays. So here's the two arrays, quick as you can. I'm going to assume you guys have found it already and determined. So here's another one. I'm going to again show you two arrays, and this time just find the two squares and determine if they're the same or different color. Okay, all right. So if you are like the participants in Sagi et al., you may have felt that the second pair was sort of easier or quicker to do. It was easier to find the two squares and compare their color than in the first pair. And the reason for this is that the first pair is structurally different, right? So even though the task was just to find one individual shape, and it wasn't explicitly about the structures here, these were different. And in the second pair, the structures were actually the same. And so structure mapping would suggest that what you do when you're comparing these arrays is, even though you only need to find an isolated shape, they are still playing a role in an overarching structure. And because the structures match in the structurally identical cases, that helps to put these two shapes into correspondence because they're in a shared role in that structure. And that facilitates making this comparison, right? So even though you don't have to pay attention to the structure, that task doesn't require that. It's still, the structure is still affecting it because when we engage in a visual comparison, we engage the structure mapping process. So structure matters here. So one takeaway from the study is that structure mapping seems to be a good explanation for how we engage in visual comparisons. But another important takeaway, I think, is that visual comparisons are spatial, inherently so, right? You can't avoid it. So for instance, in those previous stimuli, you can't really consider them as just isolated objects. Once you make something visual, it has spatial properties, it has spatial structure that affects the visual comparison, right? So these sort of spatial constraints are unavoidable if we're talking about visual comparisons. And if that's the case, then we really need to consider the spatial arrangement of these visually presented examples because it's going to potentially affect whether we are supporting or hindering a comparison. So again, I have more demonstrations for you to really highlight a particular aspect of spatial arrangement that I'm going to be focusing on today. So you can just think to yourself whether the patterns in the pairs that I'm about to show you are the same or different. So I'm going to go just quickly through here. Sorry, that last one was really quick. There we go. Okay, so here is a sample of the pairs that I showed you before. And as you were going through, you might have noticed that some of those judgments seemed a little bit easier than others. So in particular, you may have noticed that pairs like the ones at the top where the figures varied, the patterns in the two figures were determined by color in both examples were perhaps a little bit easier than in pairs where the patterns in one were determined by color and the other by shape. And this is because you not only have the structural similarity of the pattern, but also this, again, the superficial sort of perceptual similarity that's in line with the structure that makes that comparison a little bit easier. Whereas here you really only have the structure, right? The fact that these are the same color and these are different, same and different to align, and you don't have this superficial similarity sort of supporting that. So these are a little bit harder to make. And you may have also, or not, but you may have also noticed that the spatial arrangement of the pairs also matter for how easy these comparisons and the judgments were. And in particular, you may have found that comparisons like the one on the left were a little bit easier than those on the right. And we think that that's because these are in direct placement, whereas these are in impeded placement. So what does that mean? And what does that matter? What does that matter? So when you're doing this task, to judge whether the two patterns are the same or different, you have to align the two figures and you have to align the structure of those two to find these correspondences across the figures. And when you have a horizontal figure like this one and this one, when you lay them out vertically, one atop the other, the correspondences that have to be made across the two figures are really direct, right? It's really clear what goes with what. There's no sort of interference from other things. There's no sort of competition. You can just sort of go directly from one to the next. But in contrast, when you have those same figures laid out horizontally, so they're sort of next to each other, when you're making these correspondences, you have to kind of pass through other elements that are not supposed to be corresponding, right? So to align this middle star with this middle star, you're passing through other stars, and that really offers up sort of a competition for matches that are not actually corresponding, but can interfere with finding the correct correspondences. And you can see, you know, these correspondence lines are sort of all overlapping. It really is hard to discriminate and keep straight what the correspondences are. So difficult that I'll just break these out a little bit. So you can see it's just really hard to kind of keep straight what's going with what in this situation. And so this is an example of the spatial alignment principle. So the spatial alignment principle is that visual comparison should be more efficient when the spatial arrangement minimizes interference from competing matches. So like I was discussing in this layout, you're not getting a lot of competition from other matches for the correct correspondences, but impeding you are. But this isn't just about being in a vertical layout, that like vertical layouts are better, because if you have vertical figures, then the sort of better alignment is to be in a horizontal layout, right? So vertical figures get direct correspondences now in this layout instead of this one. And I do want to point out that this is not really a categorical distinction, it's really a continuum. So this is sort of the worst case scenario and best case scenario for these figures. But if you sort of put these figures on a diagonal, a sort of oblique arrangement, then you can see that the lines here, these correspondence lines, get just a little bit more confusable. You get maybe a little bit more competition spatially from what should go with what. And sort of as these angles change to get more and more impeded, it gets harder and harder. So it's sort of a matter of degree in terms of how the spatial alignment is supporting or interfering with finding those correct correspondences. So this is what the spatial alignment would predict, that we would be best in direct alignment, worst in impeded, and that oblique would be sort of intermediate to that based on how much interference you're getting from the spatial arrangement of the items. And so these are the predictions that Matlen et al. Tested in their 2020 paper. So they gave stimuli just like the ones I showed you, horizontal figures and vertical figures, either in direct alignment, impeded alignment, or sort of in between on a diagonal. And they had stimuli that were within dimensions, so both determined by shape, both by color, and also these cross-dimension pairs where you had one of each. And just in general, the patterns they found were the same for both kinds of trials. What did they find? So what they found was consistent with the predictions of the structural alignment principle, spatial alignment principle, excuse me. So this graph is showing the average error rate. So that means lower is better here. And on the x-axis, we have the conditions. So here on the left, we have direct. Participants are making the fewest errors on pairs that were in direct placement, the most when they were impeded, and then they had two versions of the oblique trials just for counterbalancing the direction, but they were intermediate, right? So just as the spatial alignment principle predicts, we see this sort of gradient of difficulty on making these judgments. And they also looked at response time, and they found a parallel pattern there. So here the y-axis is response time. So again, lower is better. And again, fastest when they were in direct placement, slowest in impeded, and intermediate in oblique. So again, these results are really, they come straight out of the spatial alignment principle. And that provides, again, more evidence that visual comparisons are being driven by a structure mapping process. But it also demonstrates that visual comparisons are being influenced by the spatial arrangement, right? And specifically, they follow the spatial alignment principle. And so that's really interesting, I think, in and of itself. How are we doing these visual comparisons? What's the process that's going on underlying that? But for the context of this talk, of course, our question is really, how do we support visual comparisons for education, right? For learning in STEM contexts. So what do we do with this information now with the spatial alignment principle? Does this matter for education? What do we do with this? So coming back to the kinds of visual comparisons that we see in STEM, a couple things I want to point out. Number one, these stimuli, right, these images are much richer, much more complex than the kinds of stimuli that were tested by Matlen et al., right? So one question is just whether or not the spatial alignment principle actually still applies to this type of stimuli. Do we still see that phenomenon in educationally relevant stimuli or not? But another question also is, you'll notice there are some examples here where we have sort of an impeded arrangement, right? So we have these two horizontal figures, they need to be compared, but they're sort of not in an ideal alignment, and others where they're sort of the way that we would place them, right? They're in direct placement here. So another question is just how much room is there to improve in education? Maybe this is something that educators and people who are creating educational materials are already doing. And understanding the spatial alignment principle is really good, but it's not going to really give us much purchase on improving education from where it already is. So those questions are the ones that we addressed in the studies I'll be talking about today. So does the spatial alignment principle matter for education? Two main questions. One, does it even apply to educationally relevant stimuli, which we addressed in our first study. We sort of roughly replicated the Matlen et al. Study using educationally relevant stimuli, namely skeletons. And then for the next question, what does this actually buy us in terms of making improvements in education? We did a second study coding textbook figures for visual comparison and their spatial arrangement to kind of see what is the lay of the land, how much room for improvement is there. So in this first study, again, it was a very similar design to Matlen et al., but we used a different task and a different set of stimuli that we took from Kurtz and Gentner. So it was an error detection task. Participants were shown skeletons like this one here, and they were told that student archaeologists assembled the skeletons and made a mistake. So participants' job was to find the incorrect bone in the skeleton and to click on it as quickly as they could. And participants were also told that sometimes they would see a skeleton sort of solo like this one, but sometimes they would see it alongside a second skeleton that was constructed by an expert and did not have any mistakes in it. So we gave this task to two groups. We gave it to adults, undergraduate students, as well as 7th grade middle school students. And in case you haven't already spotted it, this is the bone that has the error. This is not a correct bone in the skeleton. And so here's what the design and stimuli looked like. So we had skeletons of animals and humans, and we put them either in horizontal or vertical orientations. And they were shown, again, either solo or in pairs. And if they were in pairs, they were either in direct placement or impeded placement. Again, with the idea that items when they were in direct placement should be easier to align, and therefore it should be easier for students, or sorry, for participants to find the error in the skeleton. And if you're looking at these weird vertical cows and thinking that like they're a little bit suspicious, I'm going to return to that in a moment. Okay, so what did we find? Oh, by the way, this was, here's the error again. I know it drives people crazy when they can't find it. So here's the mistaken bone in this item. And this was counterbalanced within participants. So this was a within participants design. So here's what we found. On the graph, we're showing proportion correct. So on this graph, higher is actually better with our three conditions, direct, impeded, and solo along the x-axis. And first, I'll point out that in general, we found this really big effect, this really big advantage of seeing pairs instead of solo items, right? So having that comparison standard was really helpful for being able to identify that error. But we also found that amongst the pairs, there was a benefit to seeing them in direct placement as opposed to impeded placement, right? So this is replicating the effect that we saw that, in Matlen et al. With these skeleton structures, right? So this was for the adults. What did we see with the middle schoolers? So again, we see this really big benefit of seeing pairs, but we did not find the same benefit for direct over impeded that we saw with the undergraduate students, okay? So what's going on there? Well, I promised I would return to our weird vertical cows. So I'm going to do that now because I think that this will speak a little bit to those differences. So because we were using sort of natural stimuli, real skeletons, these skeletons have, many of them have a sort of canonical orientation, right? We typically see cows horizontal, not vertical, standing up on their rears, right? That's a little weird, very unusual for us to see that. And so we expected that this would make a difference in how easy it was for students, or sorry, for participants to sort of make sense of the stimuli and be able to find these errors. So we looked at this, we looked at stimuli according to whether they were presented in a canonical orientation or non-canonical orientation. So this is just a subset of the items. There were a few items that didn't really have a canonical orientation that we excluded. And reanalyze the data looking at it this way. So again, this is the adults, same graph as before, but now the lines in blue are the items in canonical orientations, and orange are the non-canonical items. And we see, as we expected, right, that the non-canonical items were just generally harder than the canonical ones, right? Vertical cows were just harder than horizontal cows. But we also found that that was not the case in direct placement, right? So when the items were in direct placement, it completely made up for the difficulties that were imposed by these sort of really unfamiliar ways of looking at the stimuli. And we see also that the benefit we get for direct over impeded is really just being driven by this these non-canonical items. And we also see for the 7th graders the same pattern. So here again, there's a cost to seeing things in non-canonical orientation, but not if you have them in direct alignment. You see this benefit of direct over impeded placement for these really sort of unfamiliar, unusual, non-canonical items. So back to our question, does the spatial alignment principle apply to these sorts of stimuli, educationally relevant stimuli? Yes. And we see these benefits are particularly for these sort of unfamiliar, non-canonical figures, things that are really counter to the experiences that students are accustomed to having. And this is important, I think, really important finding in terms of thinking about how this applies to education, because really everything is unfamiliar to novice learners, right? So in an educational context, that's exactly where students are being exposed to new ideas, new representations, new content all the time. And so spatial alignment might be a really important factor to consider in those educational settings, and where you know, sort of they're encountering unfamiliar things, and they could really use that support from direct placement to facilitate the comparison and help them make sense of these unfamiliar and new figures. All right, I'm gonna skip some of this. Okay, so So now we know that the spatial alignment principle does apply to these richer, more complex figures, but what difference could this potentially make? So we kind of broke this down into two questions. So one, just how broadly could the spatial alignment principle apply? So how often are students being presented with visual comparisons? And how often are those comparisons sort of applicable for the spatial alignment principle relevant? And then also, how much potential for improvement is there? So how broadly can it apply, but also what are the comparisons that they're getting already looking like, right? Are students already getting everything in direct placement? Are we already doing sort of as well as we can or not? And to answer those questions, we did a second study coding the visuals from 3 popular middle school science textbooks, particularly topics of evolution and anatomy. And this was led by Benji. And this comprised a total of 313 figures, which averaged about 1.8 per page. So figures are really, these textbooks are really figure heavy. So here's just a sample page to give you a sense of just how sort of dominant the visual figures are in these textbooks for middle schoolers. A lot of images and very little text on a given page is very common. And so what we coded was for each figure that we identified, we coded whether comparison was involved. So here's an example of a figure where comparison was involved. We have these 2 wings that students need to compare, and we coded for whether they were comparison was involved. For instance, this one, it was very, very clear. There were explicit cues, right? Though used for the same function, the wings are too different in structure to suggest close common ancestry. Very clear that you're trying to compare these to find similarities and differences. But there were also other cues that were used that were a little bit more subtle, aspects of the figures themselves that were used to indicate that 2 things should be compared. And then for many figures, there were actually multiple comparisons involved. So for instance, in this figure, there are actually these sort of 5 forelimbs that are meant to be compared to show sort of the opposite, that even though the functions are different and perceptually they're different, the underlying structure is the same. But here there are actually sort of 10 individual pairwise comparisons that should be made to kind of fully align all of these different items. And so we also coded for each comparison whether it was in a direct or impeded placement. These, of course, would be in direct placement here. And what we found is that, one, comparison was relatively frequent. So about 37% of the figures that we coded involved comparison. And I would argue that that might sort of underestimate how often comparison is really would be beneficial, certainly, and might even be requested of students, because this only involved within figure comparisons, nothing where you might be comparing across figures, but still more than a third of the figures involved comparison. And the spatial alignment principle was relevant for most of those comparisons. So a vast majority of them were between sort of 2 horizontal or 2 vertical units when the spatial alignment principle sort of makes the clearest prediction. So certainly we would find that the spatial alignment principle sort of has broad applicability for these figures. And we also found that kind of good news, I think, almost half of the comparisons were in direct alignment, 47%. So that's great, but that also means conversely, right, that more than half of the comparisons were not in this ideal direct alignment, right? So still quite a significant bit of improvement, I think, for being able to apply the spatial alignment principle, perhaps to make these figures a little bit better, to make the comparisons more supported. So taken together, the fact that it can apply pretty broadly, but that it's not being universally applied, suggests that there really is potential for a significant impact in thinking about the spatial alignment principle and applying it in educational contexts where students need support to make these comparisons. So just, where am I? To sum up the talk so far, we've argued that visual comparison is done via a process of structure mapping. Using this perspective, we derive certain predictions and principles from structure mapping, like the spatial alignment principle, and that thinking about these can really potentially give us some insights on what we can do to improve learning in education. And our work suggests that the studies that I just presented on suggest that there really is potential for educational impact in considering the spatial alignment principle, right? It can apply to these cases, but it's not being applied universally, right? And so currently what we are doing is, we've established that there's potential for educational impact, and the work we're doing now is really testing the actual educational impact. So if we actually try to apply this principle, what are the results on learning? And so coming back to these textbook coding results that we found, one follow-up study that we're looking at is sort of building on this, is related to these. So when you're looking at this sort of more than half not in direct alignment, one question is what's going on there, right? Are these cases where they could easily just be in direct alignment and be sort of better supported comparisons? Or is there something else going on there? Is there some reason why they're not? And this is important question because in textbook figures in particular, there's lots of other considerations, right? There's lots of constraints on the kinds of choices that textbook publishers are making in terms of the content and structure of these figures. Lots of practical constraints. Of course, these things cost money, they're for profit. So they care about things like cost and how much space these figures are taking up. So those are important considerations, practical ones. But there's also other things that are really important for the effectiveness of the figures beyond just whether the alignment is supported. So for instance, disciplinary conventions, right? It might not necessarily be useful to completely flout conventional representations just to get a better alignment. That can cause confusion of its own. Perhaps students need to learn these disciplinary conventions. So there are trade-offs, some potentially in considering these different factors. And also, textbook figures really serve multiple functions. So yes, they need to be clear, they need to convey the information in a useful way, and make these comparisons easier so that the information is more readily available. But also, we need students to look at the images. We want them to care about them. They need to be motivated to look at them, right? So there are other there is motivation to think about student motivation and not just potentially make a bunch of figures that they won't look at because they're boring or disengaged with them or whatever, right? So that said, I would argue that it is not, we saw examples that would suggest that this is not only a case of this being the best we could do and prioritizing other considerations, because we saw examples like this across textbooks. So here is an example of, these are two diagrams showing the evolution of horse forelimbs, sort of from sort of having multiple toes and multiple bones here to gradually becoming just one toe. They kind of lose their multiple toes and lengthening of the bone here. And you can see this one, in making these alignments, these are in direct alignment. You can kind of draw these correspondences very directly. I didn't draw the correspondence lines here because they would be a hot mess, right? But that's the point, that this is a lot harder to do. And this seems to be a fairly arbitrary choice, right? So here is at least one example where you could apply the spatial alignment principle to produce a potentially more effective figure. And there doesn't seem to be any cost to that in terms of visual interest or space considerations or anything like that, right? So it does seem like there is potential to improve the figures that we're seeing. And so that's sort of where we're starting with one of the studies we're doing currently. We're trying to ask, can we actually improve the learning materials, right? So given all these other sort of realistic constraints on figures and textbooks, if we just make things in direct alignment, in direct placement, does that actually improve the learning material, and do you get better learning from that? So what we're doing in this study, this is, oh, I forgot to put Sean's picture up here. Sean, your picture is supposed to be up here. We took actual textbook images and passages from the textbooks we had coded, and we are modifying the images to either be sort of in direct placement or not, and then asking whether those direct versions are actually better. So we're taking sort of direct versions and making them indirect, making them worse, and also making indirect versions that we saw and making them better by putting them in direct placement. And so here's just what that looks like, right? So here's a little passage from the textbook with an image, again, with these, comparing these sort of forelimbs. And the participants see pictures either like this, where they're in direct alignment, or in impeded alignment. And then they see a whole bunch of different kinds of content, different kinds of figures. And then we're going to ask participants sort of about their content learning. Did they actually get the information from these figures and passages better when they were in direct alignment or not? But also collecting some subjective ratings on things that are important for these kinds of considerations, right? Students' own sense of how effective the figures were, how helpful were they? Did students actually feel like they were learning more and that it was more helpful? How interested in the topics they were, given the figures, how visually appealing the images are. So factors that all seem to matter for students actually engaging with visuals in these textbooks. So that's one avenue we're pursuing. And another current study that we're working on is really sort of asking, how much can we improve learning, right? So how far can we push this? Up to now, we've really been looking sort of at limited sort of one-shot individual figures. But if we really want to have an impact on education, we want to be able to use this principle to really improve sort of more complex concept learning, things that are challenging, and really sort of infuse education materials with this principle to improve them. And so to sort of look at sort of expanded impact of the spatial alignment principle, we're looking at middle school lessons on evolution. So we've created lessons on natural selection and manipulated the instructional figures to be either spatially aligned or not. And then we'll be testing students on their understanding of natural selection. And I'm going to skip over the images. Well, maybe I won't skip it totally. It's a little, I'm not going to go into detail, but basically, here's an example of a spatially aligned, nope. Oh yeah, my computer's lagging with these huge images. All right, here's a spatially aligned version. So one of the things students struggle with evolution and understanding natural selection is kind of bridging sort of their understanding of what's happening to individual animals in the environment, right? Like this animal is going to die because it can't access food, with what's happening at a sort of population level over time. And so by aligning representations of those two aspects spatially, we're hoping that that will help students make that link versus a condition like this where that sort of spatial support is not there. So this might be more challenging. So yeah, again, in sum, I already went through all this. So yeah, I'm just gonna end it there. This is a sort of broad gloss of the talk that we just went through. So thank you to everyone.